Okay, so we thought about it for a couple minutes, and now we are ready to finish this proof. Well, if you look back at the induction step, this whole thing from here is equal to this, and you want to use that fact. So this whole thing is equal to k plus 1 factorial minus 1 over k plus 1 factorial, and we're adding on to that k plus 1 over k plus 2 factorial. And now you want to ask yourself, how can I combine these two like terms? Sorry, how can I combine these two fractions? Well, you need to times this top by k plus 2 times the bottom by k plus 2. And let's see what we get. The top piece becomes k plus 2 factorial. The bottom piece, minus k plus 2. The bottom piece becomes k plus 2 factorial. And then we're subtracting off, we're adding. Should have put it in the same. See, that's when we did this. Plus k plus 1. Well, let's simplify. K plus 2 factorial. Let's see, minus k. We have this minus k and this positive k, so that means those are going to cancel. We have a minus 2 and a positive 1, so that's going to give me minus 1. And it's all divided by k plus 2 factorial. And let's see. We were trying to prove, let's see what we were trying to prove. We were trying to prove that this is equal to k plus 2 factorial minus 1 over k plus 2. Alright, so we did that, and so the proof is done. And to finish off the proof, you say, thus, by induction, our proof is done. We're complete. And you can use that blocked in square, or you can say also Q, E, D. For example 4, use induction to prove that sum of, let's see, all the powers of 2 up to the nth minus 1 power is equal to 2 to the power of n minus 1. Well, some of you asked about sigma notation, so let's try that one out for this one. Let's write down what this would be. This would be sum of 2 to the power of n minus 1, and since we wanted the first term to be 1, that means we would need to say n from 1 up to k, and we're trying to prove that that is equal to 2 to the power of k minus 1. So base case, sum from n equals 1 to 1, so that's just one term. 2 to the power of 0 equals 1, and we're going to ask, is that equal to 2 to the power of 1 minus 1, and that is equal to 1. So done with the base case. Assume you can sum from n equals 1 to k to the power of k, whoops, that should be an n minus 1. And we're going to say, assume that that's equal to 2 to the power of k minus 1. Let's see what we're trying to prove. We're trying to prove sum of n equals 1 to the power of k plus 1 is equal to sum of 2 to the power of Okay, so I'm trying to prove the k plus 1 case. And let's try and do that. Well, this is equal to sum of n equals 1 up to k, 2 to the power of n minus 1 plus 2 to the power of k, because n minus 1 plus evaluated when n is equal to k plus 1 gives us 2 to the power of k. And we're going to say that's equal to, well, let's see, what was this guy equal to? This guy was equal to 2 to the power of k minus 1. And we're adding on 2 to the power of k from this guy. And so let's evaluate that. We have 2 times 2 to the power of k, because we have 2 of them, and we're still subtracting off 1, and that's equal to 2 to the power of k plus 1, right? Because here are your k2's, here's your plus 1, 2. Minus 1, and that is exactly what we're trying to prove. So thus, by induction, our proof is complete. See how many more we got left to do. Proof by contradiction, prove that it's irrational, x be non-zero, want to be irrational, prove x, y is irrational. Let's do, you can try this one on your own and then maybe ask about it tomorrow, just to keep it short. I think you can do it. Show that it's divisible by 6. Remember, to show that a number k, to show that 6 divides k, you need to show that the remainder is 0. Which means you need to show that k can be written as 6 times m for some m in big Z, or the integers. Alright, so that's what you need to do for this one. Proof by contradiction. Assume that the inverse of the statement is true. So if your first statement says if P then Q, inverse, right? Let's see if we remember. We need to say not P then not Q. Sorry. Let me get my facts straight here. Yeah. Actually, I don't quite agree with how that's spelled out, so let's just go through it. Prove that the sum of any positive real number and its reciprocal is at least 2. So what this says is prove that the sum of any real number x plus its reciprocal is at least 2, so greater than or equal to 2. Well, it says real number, and let's see, we're trying to come up and say, can I prove that? Well, if you were trying to prove it directly, maybe you would want to get this as the same denominator as this. Let's try that way. Let's try directly, then prove it by contradiction. That'd be x squared over x, and we would add on 1, and we'd want to show that that's greater than or equal to 2. Any real positive number, so that means it's greater than 0, so we can do this without changing sign. X squared plus 1 greater than or equal to 2x, and that implies x squared minus 2x plus 1 greater than or equal to 0. That's x minus 1 squared greater than or equal to 0. Now, x was positive reals, and if you substitute any positive real value for x into this statement here, then that means since you're squaring it, it definitely will be greater than or equal to 0. So that means we proved it directly, and so you can stop. So that was direct, and now let's try contradiction. So this was direct, which is good to know how to do, so it wasn't that bad. And now we'll try by contradiction. So assume that x plus 1 over x is, we said originally that it is greater than or equal to. Well, what's the opposite of that? Well, assume that it's not greater than and it's not equal to, so that means assume that it's less than 2 for x in the positive reals. So you're going to assume that and try and come up with a contradiction. Now if we try and think about how we might prove that that is going to be a contradiction, how do we prove that? Well, let's clear the denominator. Go through it the same way that we just did. X is non-negative, so we can do this. X squared plus 1 is less than 2x. X squared minus 2x plus 1 less than 0. X minus 1 squared less than 0. This cannot be less than 0 since we're squaring it, so that means we arrived at a contradiction. Some people write that symbol, some people write this symbol for contradiction. So since we arrived at a contradiction, you would say, for conclusion, you would say a contradiction so our assumption was false. Thus, x plus 1 over x is greater than or equal to 0. And all those words in that statement are as condensed as possible, and they're necessary. You need to say what you're assuming. You need to give proof. You need to make a closing statement. You've reached a contradiction, so our assumption is false. Therefore, you assume, or sorry, you not assume, you have proved that the opposite is true. And we end our proof there. We did this one in class, so I'm not going to go through that again. We did it with different numbers, and so you can do that. Maybe ask questions about it on Thursday if you can't do it. And example 9, let x be a non-zero rational number, and let y be an irrational number. Prove that xy is irrational.